Welcome to the algorithms course. Today we will talk about the greedy algorithms, the main concepts behind it. Very tempting idea, I must say, because as we probably all have heard, that greed is good, at least to some people, right? Especially as evidenced by Mr. Burns and Michael Douglas in the movie Wall Street. Good examples of this greed, but of course, as we all know, greed also fails. But as far as algorithms goes, this is one of the main, so to say, rules or heuristics of how we can approach algorithmic program design, meaning solving problems. And it is extremely tempting idea. We simply don't look beyond a horizon. We make so-called greedy choice, so-called locally optimal choice, meaning we don't consider much of extra beyond or just something we know immediately without extra storage, without any caching, any storing anything looking forward. Basically, we take the myopic view, nearsighted view, and somehow we hope that this approach, this greedy, this locally optimal approach will lead to, well, global wellness, and especially will solve us our problem. So again, a very, very tempting approach. So hopefully by the end of the lecture, you will see how local optimal choices are actually different from global optimal choices. I'm sure you will figure this out. Also, you will see some classical situations where greedy algorithms succeed, and also you will realize how often greedy algorithms fail. The one of the main reference for these materials is Jeff E. He's a professor at Illinois University, very good professor. He mentions that greedy algorithms are, well, they are almost never correct. And he is right. I think it's very rare that a greedy algorithm will work. It's just that it's beautiful when it works. Unfortunately, we'll see that most of the time it doesn't work. The good news for you guys is that it's easy to when you find a counterexample, you have basically disproven that this algorithm, this greedy approach is wrong. You have disproven that it's right. I mean, you have proven it's wrong. So, what is exactly a greedy algorithm? Basically, we build a solution step by step. We have to make multiple choices, right? Our algorithm have to make multiple choices, and each step we are not considering past, not looking for future, no backtracking. Backtracking we will discuss in more detail later on in the course, and we don't look at all the solutions. So, the greedy approach can be very tempting when we have a myriad of choices to make, right? So greedy algorithms have a tendency to have low complexity. Why? Because we're not really exploring all the solutions. This is not a brute force solution. It's a greedy solution, right? So, again, not always correct, or I would say mostly, usually not correct. So, again, show you a classical example here. Actual largest pass, we need to find so-called collect the most coins or collect the most life, right? And we are starting here, we have to make choice. And this is a binary tree, we have to make binary choice, choose left or right, very simple. And our greedy algorithm would always take the highest value available at the time, right? And as you can clearly see here, this would be the greedy pass, the red one, and the green pass is the actual optimal solution, right? So greedy, one thing we should mention already, that greedy algorithms, well, they usually lead to some solution. You can design a greedy algorithm to provide a solution, but again, it is not guaranteed to be the optimal path, optimal solution, unless certain conditions are met, again, which are rare, right? So this is classical example where it's not going to work. You can find a counterexample very quickly, right? So again, so you may say, why doesn't it greedy algorithm already start thinking about why doesn't it work here in this case? Well, we have basically the reason is because in this structure, each of these vertices or nodes of a graph, right, they have no particular information encoded relating each to another. Basically, we don't really, in order to get our optimal path with optimal values, the maximum values in this case, we would have to basically do a brute force search in this case. We don't really have any other option, really. I mean, of course, we'll see where we have other ways of exploring this search space, but a greedy approach is just, there's no way around it, basically. We have to look at all solutions in this case to find the optimal, because again, if you take some other approach, maybe this 99 could be hidden here, it could be somewhere else. Again, this maximum value, again, you don't know ahead of time where it's going to be. So this is a classical case where greedy algorithm will not work as far as optimal solution. It will work for a solution, excuse me. So, right, so intuition, right, again, so they rely on hope that if you make repeated global good choices, will lead to this global optimal choice. So again, we keep asking this, when is it going to work and when not, right? And if it fails, where does the reasoning fails? So let's look at some examples, right? We have some rules, right? We can print the rules. These are some helper function. So let's look at one of the earliest or more well-known problems, so-called coin change problem, where this might work, maybe not, right? So our goal is we are a cashier at a store, grocery store, and we need to find minimum coins that have to be given in exchange. Again, maybe the manager is angry at us, or I don't know, why would you want to give the least coins? But well, usually you want to give the least coins, right? So a natural greedy strategy in this case is you have some coins and you need to provide some change. You always start with the largest coin. I mean, that seems a very logical strategy, right? I mean, take the largest coin which is available, right? So in this case, you want the target 63, right? So you take 25, 25, then 10, and then 3 ones, right? I mean, seems normal strategy, right? So, but we'll see, maybe there is something is not quite right with this strategy. I mean, it's gonna give us a solution. So we call this greedy coin change, right? So we given how much we need, we given a sequence of integers, what kind of coins are available. We can add a debug flag, simple Python code, right? So let's see what we have. Do we have a code here? No, let's run it. So let's run it. Let's run it for our example. So euros. So we have, this is what 1, 5, 10, 15, 25, just some standard coin system, right? And we also have a euro 1, 2, 5. 10, 20, 50, right? And 88, right? So let's take a look at these examples. So 1A, right? So as expected, we take 25, we are left with 13, we take 10, 1, 1, 1. So how many coins? 6 coins, right? Simple to follow, works. We know it's gonna work. We're gonna have an example, right? So how about this euro, right? Let me maybe give this debug true also for euro. I'm sure you are gonna see this. I recommend you do this also yourself. Try some other changes. Again, easy to rerun. So again, we start with 50, 20, 10, 5 to 1. This is actually, of course, perfect because each coin only once. Again, but we have no limit. We have a huge change jar, right, for all coins, right? We are not limited with this, right? You can probably think of other strategies, of other limitations where you don't have all the coins, of course, right? So, and here is the interesting moment. Yes, this greedy approach, the simple approach that any cashier would appreciate, will work on most common currency systems. It will work correctly. However, this is not automatic guarantee that this will work correctly on all coin systems. So now you might ask, when does it fail actually? Right, well, when we have some funny coins. So this is very simple. You have 1, 3, 4. Extremely simple example, right? So the greed would take what? 4 and 1, 1, right? Hopefully you see the issue, right? We'll have 3 coins. Is that the maximum? I mean, is that the minimum number of coins? Well, you can already start to think of another example. You can take 2, 3 coins, right? And you have what? You will have 2 coins, right? So this is the simple example. It already shows that the greedy approach will not work for all currency systems actually, right? So, so a simple example, right? So a counter example, right? We can see this, right? So counter example, 4, 3, 1, right? You take 2, 1, 1, so 4, 1, 1. But this would have been, of course, 3, 3 would have been an optimal result, of course, right? This would have been an optimal result. So greedy change is fast and intuitive, but correctness depends on structure of the coin system, but not just on our intuition. So you might be asking whether maybe I should ask this for a extra credit, or maybe research on coin systems. There have been some real life coin systems where greedy approach would fail, right? Would fail. I mean, would not give optimal minimal number of coins, right? So, but most, of course, European, American, pretty much all around the world will work correctly. So this could be an interesting bachelor's thesis topic, actually, or maybe mathematical topic, where to explore, at least the paper-wise, to explore where, at which moments these currency systems start failing to the greedy approach. You can see something here already, some intuition. 431, I mean, right, those kind of funny coins. So if you have these two currencies, these denominations very close together, that usually implies some bad news for the greedy algorithm, right? So that's one of the takeaways. I'm just giving you some hints. Again, don't have to research, but it's interesting subtopic. So let's move on to another one. This is also a well-known approach. So we have some activities. You have start time and finish time, maybe schoolwork, maybe classes, lectures, maybe conference, where you want to attend as many sessions as you want, maybe some, I don't know, you are at a resort and you have a bunch of activities, or, but your goal is to have maximum number of non-overlapping activities. So basically, you don't want to spend the whole day in one boring activity. You want to have as much fun as possible across all activities, right? So, and this is again very simplified example. We'll only provide start and finish time. Maybe next year I'll provide also some names and some activities. You can think of some, right? So now let's think about some activities, some approaches of greedy approach. Sometimes I give some quizzes. It might be on a quiz, and sometimes on some questions. I provide some strategy, and I say, is this a greedy strategy? Well, and sometimes you students are smart. You say, okay, but this is not the optimal strategy. But again, there could be a greedy strategy which is not optimal. We already saw this with the currencies, right? So just because it's greedy does not mean it's optimal, right? And just because it's optimal doesn't mean it's necessarily greedy, right? So, but greedy strategy is always choosing something that's based on the current situation, right? Not looking forward, not looking backward. That's very, very characteristic of greedy strategy. So we could think like this: choose the activity with earliest start time. That sounds pretty good, right? How about choose the activity with the shortest duration? Right, maybe choose the activity which does not cause the least conflicts. So these are seem reasonable rules, but they actually all fail, meaning they do not guarantee the optimal solution. Again, you'll be able to test it out yourself, but which one would be the best one, actually? The actual greedy strategy that works is a little bit slightly less intuitive maybe, but it actually, if you think about it more, it makes sense. It is choose a compatible activity with the earliest finishing time. So, meaning this is the intuitive approach. If we finish early something, right, we have more time to do more, right? So again, and this means so why does this work? Let's think about this a little bit. So the reason it works actually is because at each step, the remaining activities, again, it will work because when you divide this problem, right, when you already perform some activity, the sub-problem again will be optimal. You can solve this problem optimally by doing the same thing, right? So that's again, it's kind of like the answer is because the problem is always solvable. Any sub-problem will also have this rule applied. Right, so that's a key idea, right? So let's look at the solution for this. Again, very simple. So we have some activities. We define this right at the top of the integers, right? And again, some typing. So greedy rule: repeatedly choose the next compatible activity that finish earliest. So, right? So we have activity selection, right? So Right, so we have this idea start finish. Okay, so hopefully all activities start before finish, right? This is just a sanity check. So we sort. So this is a key idea. We sort, right? We provide a lambda, right? Is sort by finishing time. So this is the key idea. So the key idea, we sort the activities by second value, the finishing time, right? And of course also we can provide the start time as second key if you want for tie breaks, right? So but key, so this is a key part here, right? Again, for those who know Python, so we are sorting by the second value, right? A very simple algorithm in Python. Again, most language you can implement very quickly, right? So we can provide, so basically negative infinity, right? And we have some debugging, and basically then the algorithm becomes super simple. Again, that's why. So that's why again shows you how seemingly hard problem is very simple with greedy approach. So start finish. So if start is over finish, right, we append this basically, right? We have sorted, right? So we check our activity, right? And since they are sorted, right? So this means is, okay, so what's happening here? We are looking through activities, and we have our current finishes when negative infinity, right? So the first activity is the one which starts earliest. So it will be added first, and so on, right? And then we only consider activities which have not yet started. That also makes sense. So very simple. And let's see if we can run it. Right, so let's say example. So 1, 3, 4. So these are the end finish times. So which one will start? We start with this one, right? And then, well, these actually are sorted, I think, already, right? But let's still, right? So we'll see 1, 4, right? These are sorted. So we take 1, 4, right? So we skip this one, right? Because we can't use it. We only took 1, 4. Skip 0, 6. Also can't use it because it already started. We take 5, 7, right? Skip whole bunch, we take 8, 1 and 12, 6, right? So we chose, these are the 4 activities. And again, you might say, okay, is this the optimal solution, right? Is this the optimal solution? Again, so it's harder to prove absolutely, but the idea is that we can do a counterexample, right? Try to see, we suppose with some activity, right? If we chose different compatible activity, right? So replacing this, right? If we started with different activity, or greedy approach we would be able to have some exchange. We would be able to still perform these activities with A, right? So there must be an optimal solution that begins with a greedy choice. So this is basically a step by step. We can always, or this greedy approach will always leave the maximum room for the later activities, right? So this is the actual solution. Again, I advise you to play around this. Again, to do, try different starting and finish times, right? So also to do too, add the activity names for next year's example, right? So maybe next year there'll be better examples, but hopefully you see this idea, meaning that we had a tuple, we had a name for this. Okay, so now earliest time, right? So we start earliest, right? Wrong example, right? You only got one activity, right? So blocks almost everything, right? So let's take a look at this, right? So yeah, so hopefully you can see this again. If this solves it, so you see our activity selection, right? We solved it correctly, right? You can see this immediately. But if we chose this one incorrectly, starts earliest, we would fail. I mean, obviously. So, and again, I'll leave this open. Try the other greedy approaches, right? Such as minimal conflicts, and also there was a third one. Again, I forgot which was shortest duration, which also is, again, it's a greedy approach. but it's not, but not the one, not the correct one. And also shortest duration. Just duration. See how they fail. All right, and now we can move on to the third, also very famous problem, or actually two problems. We are given a knapsack, which is a knapsack, or a backpack or a box, and we have two things. We have a value, right? We have a whole bunch of items with value and weight, and our goal is to maximize the total value without exceeding weight capacity. So think of, you went to a trip abroad, right? You're already abroad and you want to bring some gifts back home, right? And you would want to maximize how much you can bring, but of course airlines have weight limit, right? And in this case, of course, sometimes there's two versions of problems. You can take fractional items, right? Half a headphone or half a computer. I wonder how that would work. But or 0 1, where you can take it or not take something. You cannot take so similar items, but greedy behavior will be very different. So greedy strategy, I think you all can think of it, is not take the most expensive thing or not take the lightest thing, but take the best deal. If you go to a supermarket in most of Europe, and I think most countries, usually there's a regulation that you need to provide the price by kilo or price in 100 grams, so we can make informed decisions, right, in a supermarket. So here's the thing is, right, we would do the same thing here. We would provide sort items by value weight ratio and take the best deal first, right? That makes sense. So again, we'll see how this actually again might not always work for one of these problems. You could probably think of which one is going to fail. Well, one of them it will fail. Right, so fractional knapsack, right? So we'll see this one here. We have item, string, float, name, value, weight, right? Okay, item. Again, very simple Python. We don't do any classes here. So fractional knapsack, right? Sequence, capacity, debug, right? So that's capacity is how much weight we can hold, right? And we provide items. So this is a greedy approach. If capacity is less than 0, we can't have a negative capacity, right? And all weights must be positive. So these, of course, are just some error checking, right, for you guys. So idea is very simple. We sort the items, right? We provide the by ratio, right? So we sort by best deal. So sort items by meaning best deal. Yeah, okay, AI is asleep, so I have to do everything myself. Right, so if the bug, right, capacity. So we will see this again, and we keep taking, right? We take as much as possible. Again, there's no limit of how much stuff you can take. So, and do we have examples? So let's look at this here. Example: gold, silver, bronze. Okay, great example, right? Especially relevant to today's age, right? So 60, 10, right? 100, right? So I forgot which one was which already. So name, value, weight. Okay, yeah. So weight. So name, value, weight. But again, just pretend this actually makes sense, right? So which one is the best deal? Looks like they actually gold, right? Because, as we all know, gold is heavier than silver and bronze, right? So you get the most value here, right? So you take as much gold as you want, right? So if you have capacity 50, right? So, well, and we have how much weight? 10, 20, 30, right? So what do you think will happen? Intuitively, it's already sorted by the way already, so we'll take as much gold as possible. We'll take 10 units, 10 kilos, I don't know, it has to be heavy backpack. I'm sure the costumes would take some issue with that, right? So a silver will take 20, right? So then we'll take 20 bronze. That's what I'm predicting. Again, I have not yet run the algorithm, well, I ran it a long time ago. So let's run it again, and we will see this exactly happening. So we have our deals, right? 6, 5, 6, right? Let's say 6 euros per kilo, I don't know, or per gram, I don't know. Well, obviously per gram, right? Could be fake gold, right? So we take 1 unit, right? Max, so we take, one maximum unit, right? Which is 10. So we are left is 40 kilos or whatever, 40 grams, right? Or a tiny knapsack, right? And 20 silver and then we take, right, we took all the bronze we could, so we took what? So we chose 100% of gold, 100% of silver, and 66.6666 repeating percent of bronze, right? So this is actually, this is a case where a fractional knapsack can be optimally solved using greedy approach. So that's a good news to you guys, right? So why it works? Best, if the best remaining item does not fully fit, we can still take the exact fraction that fits. So this means the ratio or ratio-based greedy choice is safe, no matter, again, no matter at which moment you take it, right? So very, very safe. Again, try it again with different items. You can just provide something else, right? You can provide, I don't know, wood or whatever, iron, right? Play around with this. Again, you can give bigger knapsacks. It will work with anything, assuming, of course, they are positive and, positive values. So now, yeah, as you already imagine, as I had told you, if it works for fractional, it will fail for 0,1. And again, this is deceptive because first of all, 0,1 knapsack is very hard problem. Actually, computationally, it's considered a NP. Let's see, it's NP hard problem. So computationally not solvable in extreme cases, but generally you can solve it, right? So let's look at this 0,1 rule, right? So counter example would be here, right? 6 capacity, right? Let's take a look at this here. Which one is the best deal, right? 30. So which one would we take here? We take this one, right? And we take this one, right? You see, this is a problem issue here already. And by the knapsack, even here you can see how it would fail. You take A and B, right? And C would not fit, right? Because we only took 30 kilos or 30 grams or whatever you want to call it. However, the optimal solution in this case would be taking A and C, right? We would have to, I mean, it'd be a little bit heavier, right? But still under the 50 limit. It'd be 40, right? And we would have extra 20 euros or I don't know what you want to call it, Bitcoin or whatever, right? Worth it, right? So optimal solution is B, well, even worse, actually. I wasn't even paying attention. Actually, optimal solution would be B and C, actually. You see, yes, you have to skip 8 completely, even though it's the best deal by far. But we can fully load this 20 and 30 in this case. We had 220, so even my example. So, greedy solution will take 60, 10, 100, but the actual solution will be B and C. And unfortunately, you say, okay, right, okay, can we have some other greedy choice? Unfortunately, there is no good greedy choice approach, right? So again, this remains to do explore how different approximations for solving 0,1 knapsack have been tried over the years, right? So again, hard program. So again, this is computational, hard problem to solve. All right, so not solved by greedy, not optimally solved. Again, solvable but not optimal. So this is now we have the last two problems are not maybe so great as far as maybe seem less practical. I don't know, but minimal points to cover, right? So meaning you have some numbers on a line, choose the minimum number of points that would cover all intervals, right? So it's kind of similar to this activity covering, right? So you want to cover like when you want to hit, I don't know, hit some again conference or some show up your face to some party, right? That you will be there basically, right? So the greedy approach is we sort the intervals by their right endpoint. Again, choose the right endpoint for the first interval, remove all intervals covered by that point, and repeat, right? So right endpoints. So that's a greedy approach. Minimal size of points, right? And let's see if you have some ideas. So we have 1, 3, 2, 5, some points on a line, right? And we want to find which points. Again, in this case, there could be multiple solutions. By the way, I should warn you on this problem. So let's print out which number. So we have 3, right? So we choose point 3, the ending point for 1, 3, because we have to cover it, right? So greedy idea makes sense, right? So we sort by the endpoints, and this one we have to cover this interval, 1 to 3. So 3 is, we have to use it, right? Then 2, 5 is already covered, we don't need it. 3, 6 is already covered. We assume endpoints and beginning points cover it, right? Then we have left is these 2, so 9, right? And here you already see this that you could take also, again, this is a little bit more flexible problem. We could have chosen 8 right here, right? When you have 2 points left, we could choose 9 or 8 or 8.5 if you allow non-integer value, floating point values, right? So it's not greedy algorithms. In cases they might give you the optimal solution, but not the only optimal solution also, because in this case, for this problem, we could also sort, there's some other ways we could sort it. So it works because when we pick the right endpoint, right, we cover it. We have to cover it, right? That's this particular example, but we preserve the maximum freedom for the following intervals, right? Because again, if we went forward, right, we would miss it, right? And left, right? So again, in this case, going left is useless. So 2.9 or 2 here would be useless, right? I mean, in this case, you can see why it would not work, because if you chose 2.9, it would lead to this interval not being covered, and we would lose out. So this is perfect example where choosing 3, the furthest interval, right, we would choose that. We have to choose it, right? So sometimes, of course, you can be more sloppy, but in this case, you have to be very precise in greedy approach. Okay, so maximum number of distinct summands. So this is an interesting, also another problem, more sort of math theory problem. So you're giving integer, right, and you need to find the maximum number of distinct, right, positive integers. So what's a greedy rule? Greedy rule is simple. Always takes the smallest unused positive integer. So when we start, we take 1, we take 2, right? So, and then of course you say, because what happens if we take 3? Well, then it will not work, because we have to take also, and then we would not be able to complete, because we're not allowed to take 2, right? So smallest unused positive integer that still allows the remaining sum to be complete with larger distinct number later, right? So let's take a look how this works actually, right? So we start, well, remaining integers, right? We have a list of summands, right? We provide with integers, right? On next value, right? And remaining, right? So let's take a look, right? And of course, so idea is this, right? Always maximum number. So what happens? So let's think about how this works. 1, 2, right? And then if we have 2 completed, right, then we take it here. At the moment we take the 5, right? Because we cannot take any smaller, because we don't have any other numbers. So let's take a look at this here, this approach, right? Right. So we have 8. So take 1, remains 7, right? Take 2, remains 5, right? And we don't have take final summand 5, because we have it there, right? We have to take it, right? So summands 1, 2, 5, right? So choosing smallest summand, well, again, leaves as much room as possible for future, right? So because again, at the end, anything left over, we can absorb it into the final without breaking distinctness. So again, the reason this is kind of silly problem, I personally don't like this problem too much, is because distinct summands, I don't know whether this would be actually useful, right? But let's go back to generalize all of this what we learned today. So 2 ideas. It's always these ideas. The first one, which is I think easiest to grasp, greedy choice. So we make the locally optimal choice first, right? And in order for this to work, after this choice, the sub-problem, the smaller problem, should again be solvable by this optimal greedy choice property, right? And again, in this course, we're not going to go deeper into this proving greedy choice, because it actually gets really messy, right? But you can prove it by using exchange arguments, right? And some structural reasoning on particular domain-specific problem. So, greedy algorithms will fail if some early choice blocks some better combinations, right? So problem does not have this greedy choice property, right? You cannot come up with a good rule. That's rare. So local optimality, right, conflicts with this global optimality, meaning how we saw this part here when we choose these values, right, in beginning, that this actually conflicts with the global solution, right? So it's also very similar to hill climbing. You probably very often used, right? Greedy thinking, by the way, used in machine learning, large language models, optimize a lot of hill climbing actually. So greedy choice, right? So we go to the better neighboring solution, right? It works well, but can be stuck on local optimum. I don't know if I have a value, right? But we always go where where our slope is higher, right? Highest slope value, differential, right? So again, but as you can probably see this, right? That's not always going to lead to optimal solution. Maybe I'll show you to finish this lecture, right? So let's do some paint jobs, right? So if I have a hill, right here, all right, something like this. And if you are here, right, and actually let's say here, you will go here, right, and you will get stuck here, right? Local optima, right? So not here, and this is max, global max, right? So hill climbing, so greedy approach, we always take the slope and we go up here, right? And we get stuck here, right? So there are ways of solving this. This will be a discussion for another, of not trying to solve it using like simulated annealing, things like that. But this will be a discussion for another lecture. So again, you can see again intuitively, hopefully you can see how this can, you stop at this local value and don't move to the highest value. So let's summarize this whole thing. So greedy algorithms are powerful because they are they are very simple to implement compared to many other algorithms, right? But that the simplicity, unfortunately, does not guarantee their correctness, right? So greedy algorithms is only as good as structural reason that justifies local choice. So when you have a problem, see, maybe there is greedy approach. Again, if this is a job interview where you have a problem, you see, okay, here would be a greedy approach to solving. And you see, okay, this will give you solution, right? But as soon as you can find a counter example, you have this proven that, yeah, this is not the optimal, the best solution. So there's some other cool things. Some of them we will cover later on in class, such as minimum spanning trees and Dijkstra's algorithm for graphs. But there's also things like Huffman coding, a very cool string compression algorithm, right? It also uses the greedy tree construction, right? So again, some play around with some coin system where you fails. Maybe you can modify the code to reject activities. Maybe do some brute force for some of the small activity selection instance and compare it with the greedy answer. That's another thing, right? As I say, or actually not only me, but many others experienced people say, when in doubt, you use brute force first, right? See, of course, that's going to be computationally much more expensive, right? But that can sort of maybe guide you on your way, right? So prove correctness, that's probably going to be hard, right? And see also where this max distinct summands return exactly 3 summands. This is, of course, just exercise for yourself. You don't have to submit them, right? So I'll see you in a lecture after this. We'll talk about dynamic programming, where we start utilizing already some knowledge. We start building solution by considering what we have done before already, in a way doing some caching as well. So thank you everyone, and I will see you in the next lecture.